I'm recording. Landon, I'm recording. He nodded. Hello, students. I'm down in the game studio. I want to show you how to visualize these two data files we've collected a little bit more cleanly and betterly before we get into collecting more data files and actually running an analysis of an experiment. Just to recap, our hypothesis is that the trait called dominance, which determines the order in which the aliens enter the field of play, is under selection. It's evolving due to selection in the game. And in previous videos I showed you how to make simple graphs of dominance, and then I showed you how to turn off the fitness functions and run a replicate of Darwin's demons that can be used as a control. So we used all of the same settings, same ship, everything like that in the two replicates. It's just that one of them had the fitness functions turned on, so their probability of having babies was related to how good they were at shooting you or getting down to the bottom of the screen. And then when you turn the fitness functions off, their probability of having babies is essentially equal. We randomly draw parents out of the population. So it's random mating when you get to that. When Craig teaches you about Hardy-Weinberg equilibrium. Random mating. So what we have here are two data files. You can see them here in the environment window. And I sort of clumsily made two different graphs of dominance. So this is dominance from the first data file when we had selection on, and our observation was that dominance values tended to go down over time. And then when we turn selection off, it kind of looks like they stay flat, but comparing these two graphs like this is pretty bush league. We can do way better in terms of our visualization. And that's the goal of today's video, is to kind of do a little bit better in terms of comparing these two graphs, set up our basic comparison for dominance, then we'll call it good, and then I think the video after that will collect a bunch of data and kind of finish off this first preliminary experiment, at least in terms of data collection. Alright, so I'm in our studio. We've set our working directory. We're using ggplot. We're plotting one or the other data files. I'll remind you what these commands do as we add to them. But one of the advantages that we have when we work in an environment like R over something like Excel is we can do sort of bulk manipulations of all of the data. So between our two data files here, we have like 2,600, 2,700 rows of 59 variables. That's a lot to keep track of. And when you do actual experiments, you're going to do, say, 3 to 5 replicates for each condition, and so a typical experiment could have 6 to 10 data files, each with thousands of aliens in it. And at that point, the code I'm about to show you today, or whatever in this video, if you're binging them all on the same day, it scales up to that. It doesn't matter how many data files you have, it scales up. So we are going to, I'll go over here and call up my notepad so that I make sure I write this code correctly. What we're going to do is give ourselves a little bit of space, and I'm going to write some lines, and I'll explain as I go what I'm doing, that will read in all of the data files in our working directory and manipulate them and put them all into one master data file. So the first thing we want to do is set up what's called a data frame, and it'll be empty. It's going to be a container in which all of our data are going to live, and I'm going to cleverly call it all the data. Okay? That is our container, and the first thing I'm going to do is just create it. And so a data frame in R is, just think of it like an Excel sheet where it's like a big table with rows and columns. That's a data frame. Although data frames are very powerful, in each cell in a data frame can contain lots of different things, not just text. But at any rate, what we want to do is set up an empty container that eventually will contain all of our data. So I'm calling it all the data. This is code that our old genomics core director wrote for me. He showed me how to do this, Sam Hunter. He's now down at the University of California, Davis. Anyway, so we're going to create an empty data frame. I'll go ahead and hit Command Enter, and shows you. So I have created something under data called all the data, but it's empty. 0 observations, 0 variables. That's what this empty parenthetical does. It's empty. I could put stuff in there, but I'm not going to yet. The next thing we're going to do is read in all the .csv files that are in our working directory. And to do that, we're going to write a very simple loop. Those of you that have programmed before know how loops work. It's called a for loop, and so we type for, open a set of parentheses, and I'm scanning over here so I do this correctly and don't make any typos. I'm going to create a variable called CSV. This could be anything. And we're going to say for all the values of CSV that are contained in, and then this is a command called dir. It's the directory command. And in fact, if I go down here and I just type this, it shows you these are the 4 things that are in our working directory right now. I saved a workspace, so don't worry about that. This is the name of our script, bio315dd1.r. It occurs to me I should start pasting these scripts into like the YouTube comments. Maybe I'll start doing that. That probably is helpful for everybody. So you can cut and paste the code and really see what I'm doing. And then I've got 2 data files, data 910 and so forth, data 93, and they're both .csv. Right? So for all of the values in the variable CSV in, and then so in the directory that we have, and then I'm going to put some information in here because I want it to only look at the .csv files. So I'm going to type pattern. I'm just telling it the pattern that I want you to look for, and then we'll put some quotes in here. Star means anything. Like a star means wildcard. It could be, a star represents like, could be anything that has a .csv extension. So anything .csv. Alright, and then because it's a for loop, we want to put those little curly braces there, and then I'm going to hit enter a couple of times. And so now what I've got is, hey, I'm making a for loop, and the loop variable I'm going to use, I'm going to call it CSV, and for all values of CSV in the directory that fit this pattern, that are .csv files, and then these curly braces mean do some stuff. For everything that meets these criteria, do some stuff. So now we have to tell it what do we want it to do. And really what we want to do is read in every CSV file, manipulate it a little bit, and add it to our big container called all the data. And you'll see why that's important at the end of this video. So I'm going to just type D. Oh, and by the way, I should explain this. You'll see me do this a lot. See this operator here? It looks like a left pointing arrow, and I make it by going the left less than sign and a hyphen. That's an assignment operator in R. So that's saying I'm writing, so here's a new thing. I'm just giving it a temporary name called D. I could call it Barry. I could call it Bio315. I could call it Cthulhu. I could call it Landon, but then he would get mad at me. So I'm just calling it D, okay, for data, I assume, whatever. And then we're going to run this command called read.csv. This is actually what R was using when we clicked import dataset from CSV. Read.csv, and you're going to read in whatever is in this container, CSV, this value, comma, as dot is equals t, so that's just a thing that's just like read it as it is, and we're going to tell it that the CSV file has a header. So a header means the column titles, the column names are in the data file. Okay, so we're saying, hey, for the first value of this variable CSV, it'll be the first data file. Read it in as it is. Don't manipulate it. There's a header, so watch out for that. It'll automatically assign that first row then as variable names. And so it'll read that in, and then what we want to do, I want to add some metadata. Okay, so I'm going to create a new variable in this thing called D, and I'm going to call it file. And to that, I'm going to assign the value of CSV. And what this will do is this will read in the first CSV file, and then it will say, I'm going to create a new variable called file, and I'm going to put the file name into that variable. And so that will allow us in this big all the data container to differentiate between the two files that we're reading in. So I'm going to create this new variable called file, and then I'm going to do this. So here's all the data. So I can hit tab because it's auto-filling. And we're going to add to our container all the data, this thing D. And what we're using is a command called rbind, which stands for, I think, row bind. And what it means is keep the column structure the same and just add all of the new rows of data to the previous thing. And so we're going to say rbind together all the data, comma, D. Okay? So what it's saying is, hey, take all the data, keep the variable structure the same, add D to it, and then it will go back and loop it again, and then it'll get the new file, and it'll make that D. It'll add the file name to the variable called file, and then this rbind command will add it to the end, and it'll just keep growing and growing and growing and growing until we've added all the data. Now I'm going to add a little kind of bookkeeping command right here I like to use. So just when you start reading in tons and tons of data with this little for loop, I like to know sort of its progress, and so every time it loops through, it'll print the value of CSV. It'll tell me what it's reading in at the end. Okay? So, I said okay again. Landon, that's like the worst verbal crutch I have. It's okay? 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 We need to set this up on like a live Twitch stream where you guys can shock me when I say it. That'll help. That sounds really creepy and weird. All right, let's see if this works. So, just to recap, we've set our working directory to be a directory in which we've copied from our Darwin's Demons data folder to a place in our directory structure where it's easy to get to, and our R script is saved there and so forth. So we set that as our working directory. We've loaded up this library called ggplot2, which is a nice graphing library that I kind of know how to use. I'm trying to teach you guys how to use it. It's very powerful. Then we create a bucket because we're going to load more than one data files, more than one CSV file. And so this command, all the data, gets data.frame, empty parentheses. That just creates an empty container to put stuff in. And then we run this for loop and we say, look in our working directory, get all the CSV files, read them in, and make this new variable called file and stack them all on top of each other. And so if we highlight all of those rows, all of that loop. Now don't forget, I ran this all the data command. I can rerun it. But highlight all this new code and hit Command Enter and we'll see what happens. You get an error message. Oh, I know what it is. Haha. I think probably I have to go back and restart everything now. Alright, so I had an error. It was horrible. Let's see if this works. It did. All right, I'm going back in time now. The one thing that we had to fix was I made an error, and what I forgot to do was I had to put this new variable name called file in these square brackets. I had to put it in single quotes. I forgot that. Okay, so you put that in single quotes, and I'll put this code into like the description of the video and in the YouTube video description, and probably on the BBlearn video description, so that you can just cut and paste the code. And in fact, right now I'm going to save this as, let's call it 2. This is our new version of our code. Okay, so we're saving this as version 2, and I'll put all of this in the thing so that you can kind of paste it in, and then it should work. But let's just walk through what happened now that I've fixed that error. And boy, oh boy, I don't think I'm going to edit out a lot of that error stuff, because this is going to happen. So let's go back up. It said error in this assignment of .data.frame, value equals this, and it's like, well, I don't know what this error means. Okay, it's sometimes our error messages are hard to interpret. And what I did, and this is often what's going to happen, is I retyped this, and what I have is like code that was working from another program over here on my other screen, and I'm like, okay, it worked over there, it's not working over here, compare what's going on. I see, I forgot to put that one thing in. Welcome to programming. That's how it works. So alright, so we created the container, we started looping through, we read in the first CSV file, we created a variable called file, we added it to all the data, and then we printed the file name. And so if you scroll down here in the console, the first file name it printed was 9.10.15.12.csv. And now if we go to all the data, okay, it looks like a Darwin's Demons data file. It's got the ship and all of this kind of stuff, all of these incredibly weird and esoteric variables that we're analyzing. And I'm scrolling to the right, and I'm scrolling to the right, and lo and behold, in all the data, it has a new variable called file, and look, it's in there. Every single observation has the file name that it was drawn from, data 9.10.15.12. And look, all the data, 2,717 observations of 60 variables, and each of our originating data files has a variable number of observations of 59 variables. So we've added a variable to the end. Alright. And then, once it was done, it went back and it found the next CSV file. It read it in, added this variable called file, and then appended it using this rbind command to the bottom of all the data. And then we printed it out, and it added in 9.3.13.37. And so if we look at all the data and we go scroll to the bottom, the file value should be 9.3.13.37. And so if we scroll all the way to the bottom, 9.3.13.37. So what we've done is we've read in both data files, and we've created a new variable so that in the master data file called all the data, we can differentiate from which replicate the data originated. Now, let's put that to some use, because we would like to compare the pattern that emerged in terms of how dominance changed over time as a result of which file it was. So, we're going to go to ggplot now, and instead of using one of those two data files, let's print, or let's graph from our data frame called all the data. And we want to do the same thing. We want to remember this, so ggplot has an aesthetic, how the graph is laid out and how it looks, and then geometries, the data that you plot on the aesthetic. And so our aesthetic is, on the x, it's very simple. On the x-axis, put the variable generation. On the y-axis, put the variable dominance. Right? And if you recall, if we just do that, that's what happens. It just says, here's what it's going to look like. We haven't yet put the data on there using the geom command. And that's what this is. So if we wanted to, we just want to plot all the points, every single observation is one data point, we just use geom point, and that's what we're going to do. And we're going to plot 2,717 data points of dominance values against the generation in which they were created. Go back to OBS here and make sure you can kind of see. I just realized my stupid ugly face is blocking generation 18, but I guess whatever. It's not like I'm trying to make a YouTube fortune here. I'm just trying to teach you how to do some stuff. So if we just go to the end of this grouped command, these two lines are united by a plus sign. And I'm just going to hit Command Enter. Now we've got a really funny looking graph. We're not there yet, but let's zoom in on it. Remember, you can click zoom and it will make the graph a bit bigger. And so this isn't really doing much, right? It's like, wait, okay. It's because we plotted the data from both replicates without differentiating them in any way, all in the same graph. And so what we're seeing is like, okay, we have this sort of pattern of dominance is kind of going along till about generation 10. Remember I told you in the last video, if you do fewer than 10 generations, very likely you're not going to see significant evolution. Generation 10, and then we're seeing at the very end here, about generation 13, 14, and so forth, we're seeing a split in the data. Okay, there, said okay again. Kill me now. Holy man, that is hard to get rid of verbal crutches. If you want to lower your self-esteem, by the way, although maybe in your generation this doesn't apply, age yourself to the age of 49 and then make a lot of YouTube videos and watch and listen to yourself constantly. It'll really, really take you down a peg, let me tell you. Our hypothesis is that under normal conditions, the trait dominance in Darwin's demons is under selection. And if our hypothesis is true, then the pattern of change of the trait dominance over time will differ when the game is run under normal conditions compared to when the game is run under control conditions, when selection is turned off and it's just random mating. But right now, this graph, it's like, okay, which is which? I don't know what's going on. So let's add some information to this visualization. I'm gonna hit save there. Okay. The simplest thing that we can do is we can add an aesthetic to the point. There's lots of different ways to do this, but I guess I'll do it this way. So let's add an aesthetic to the point geometry. And let's say color equals file. Okay? Remember we put a variable. Now, by the way, the variable name file isn't very smart because file actually can be used as commands in some context in R, but I'm never said I was a smart programmer. I just want to help. So all I'm going to do is I'm going to say, hey, I've got two different data files in here. Make them two different colors so I can see what's going on. All right, are you ready? Do you have a prediction in your mind? Which is which? Oh, haha! You thought it was going to work, but it didn't, and I don't know why. We've got two different files in our all the data container, and we would like to differentiate them visually. The easiest thing to do there is to just make the data from each file a different color. And so what I've done is I've added in this aesthetic command x-axis generation, y-axis dominance, comma. I hit enter here just to put it on another line because I don't have a lot of real estate in my script window. R doesn't care about having enter and stuff like that, so it'll just automatically go to the next line. And I added color equals file. In this case, it's the variable file. So what it's saying is make each file, the data from each file, a different color, and then put the points on the graph. And then we hit Command Enter, and now we've got a multicolored graph. And if we zoom in on that a little bit, you can see already that maybe these data are consistent with our hypothesis. We still have some statistical tests to do, but here's the value of dominance for two separate data files, two separate replicates. The one in which selection was turned on was the 9-3-13-37 one. The one where selection was turned off was 9-10-15-12. And you can see when selection is turned off, it sure looks like the dominance value stays relatively flat. And when selection is turned on, the dominance value tends to go down. Now, I'm just describing it in sure seems to, tends to, looks like. Clearly that's insufficient. We have to do some summary statistics and statistical analyses, but I think this is enough for this video. So what we've done is we've ingested two data files, added some metadata about those files so that we can use it later when we graph it, and then differentiated the patterns of the two files on the same graph using color. Let's do one last thing before we call this a video. So I'm going to get out of here. There's another way that you can do this if you want to sort of separate out the two conditions. So you can facet graphs in ggplot. So in this case, I'm going to do facet wrap, which means it just creates a series of faceted. We'll only have two conditions, so it's fine. You can do this in grid and things like that. And what I'm going to do is I'm just going to say facet this set of information by the variable file. And in this case, it makes two graphs, and we'll zoom in here. And it puts each file on a separate facet. And so sometimes, because before our graph was, they were like graphed on top of each other, and it was sort of hard to see what was going on because one set of points was obscuring the other. Now I've made it on two separate graphs. They both are scaled the same, so they have the same x-axis and the same y-axis. If you did these separately, if you recall, we did each one using a separate data file. What happens is the programs that you use will generally auto-format the axis to fit the data. So the scale will be all weird. This one will be like from 5 to -15, and this one would be from 5 to -6, and then it would look strange. But now they're all on the same scale. Very easy for you to compare, and it's very obvious that there's something different going on between the left and the right panels. And again, our hypothesis is that result, that pattern, is driven by natural selection. Is this sufficient to prove that? No, because we don't know if these, we've done this exactly twice, and we have no idea if these results could have occurred simply by chance. They had nothing to do with turning selection on or off, or the fitness functions on or off. Could have happened solely by chance. So how do we deal with that? How do we know when the differences we're observing are not due to chance? That's statistical analysis, and we'll do that soon enough. And we get to that with replication. We can't just do one run like this and one run like this and say, oh look, dominance is under selection. That's like saying I saw a blonde woman and a man with brown hair, therefore men have brown hair and women are blonde, right? You need replication. So let's call that a video, and I'll post this, and then we'll do the next one. Okay, okay, okay. I'm saying okay a lot. Okay. Landon, say okay. 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 Bye, everybody.